Guys ready? Like by the time we get to the end of these slides, that will undoubtedly be on Tuesday, not today. Then again, you'll have like the single best and simplest method for doing state space tracking ready. You guys will be ready to start working on your projects and doing all sorts of fun things. So we're getting there. This is in some respects the highlight of the class. Do you guys have any questions on the Monte Carlo integration that we talked about before we go on this? Okay. Here's the overview. So what we're really trying to do is a lot harder in a lot of respects than simply doing a Monte Carlo integral. We're trying to track a nonlinear, non-stationary system and do it in a way that's optimal, or at least approximately optimal, or I should say asymptotically optimal. The fundamental algorithm for doing what's sometimes called sequential importance sampling, you now can probably understand at least the term importance sampling, because we had the importance density. When you draw samples from the importance density, basically when you run your random number generator, that's importance sampling. You're sampling from the importance distribution, and the sequential part of this is you'll see in a bit, but we need to be able to do this sequentially in order to be able to track without having computation just scale with time. And so being able to do that basically recursively, recursive importance sampling might be a better way to express that. So we're going to be talking about this, and the fundamental algorithm relies on Monte Carlo integration. It has a lot of different names. Probably the most common name is particle filter, but it has other names as well. Some people call it sequential importance sampling. Sometimes it's called sequential Monte Carlo estimation. And now that you know about Monte Carlo integration, you can guess why it's called sequential Monte Carlo estimation. It's also called sometimes bootstrap filtering. Condensation algorithm was an early name, as was survival of the fittest. But particle filtering, sequential Monte Carlo methods or estimation, sequential importance sampling is usually used to describe a specific type of a sequential Monte Carlo algorithm or a particular particle filter. So just a little bit on the terminology. It's a little confusing, but it's gotten a lot better with time. So particle filters, sequential Monte Carlo methods are the two most common. You'll recall when we were talking about optimal Bayesian tracking that we had one of two goals. We either wanted to estimate the marginal, which was the most common thing, or we wanted to estimate the joint. And it'll turn out the particle filter will give us both. Let's assume for now that we're working with a joint, and let's assume, just for the moment, that our joint posterior probability an approximation of it can be written as this weighted sum of impulses. It shouldn't be a surprise. The weights, of course, have to be scaled so that they sum to 1, so that when you integrate this thing, it integrates to have the value of 1. So we've got a weighted combination, a weighted average of impulses. The one nice thing about this representation that I didn't mention before is, in general, when we're thinking about this posterior that we're trying to track, especially this thing, one of the things we try to drive home is if you've got this multi-dimensional posterior that's growing with dimension, it's growing with time. You start off at time 0 and it's got a dimension m. At time 1, it's got a dimension of m squared. At time 500, it's m to the power of 500. It grows exponentially with time, I think, if I'm thinking about that right. It's bad, and thinking about how to represent that mathematically is like it's difficult to even think how you would represent something like that. But with this weird representation of posterior probabilities or probabilities in general as this weighted average of impulses, suddenly it becomes manageable, because the only thing we have to worry about are the weights and the trajectories of the particles, the samples that we've drawn. And we know from importance sampling that we're going to draw these numbers from some kind of random number generator. we will pick what those are. So the only thing we really need then are the weights in order for this whole thing to work. So we suddenly took something that's really difficult to handle, really nasty, and now we've narrowed it down where if we've got n sub p particles, all we need is to know those trajectories and those weights, and we're done. And the weights are scalars, so they don't even grow with time. So it turns out to be quite a tidy parameterization of something that seemed like it was so intense and in such a high-dimensional space that you couldn't even do that. Okay, we're going to start to get into some fine points, and the math is going to get a little intense. It's not so bad this lecture, but it's going to get intense shortly, and then it will get a little bit better again. So I need to explain something that is glossed over in a lot of the articles and even in the book. They start off in a lot of the references where they're trying to teach you about particle filters, and they say, oh, the importance density that we're going to work with can be factored as a product of these two things. And if you look at it and you're like, well, wait a minute, I know Bayes' rule, and if I were to factor this by Bayes' rule, the way I would factor it, if I wanted one of the terms to be the marginal of the state at time n conditioned on y of 0 to n, the other thing that was already conditioned on, plus what we're not doing the marginal part of, that would be what's left, which is the state from 0 to time n minus 1, it would be this term. And then the other term that's remaining would be what we sort of conditioned out, which would be the remaining state from 0 to time n to n minus 1, conditioned on what was to the right, which is the measurement from time 0 to n. And yet, when you look in the articles and you look in the books without comment, they factor it this way. And if you look at it carefully, one of the differences is that they have an n minus 1 instead of an n. And like, well, where did the measurement at time n go? I mean, it was there. It's right there. How come it's not over here? You know, suddenly it's n minus 1. And the answer is that the people that are teaching you about particle filters, the authors, if you will, are actually making a design decision quietly without telling you about it or telling you why they made it. And because this importance density is something that you get to pick, the authors that are trying to teach you about particle filters made a choice that they're not going to condition this probability on the measurement at time n on purpose. And the reason that they do that is that ultimately they want this thing to be expressed in a manner in which they can advance the particles recursively. That if they know what the particles are up to time n minus 1, that they don't have to recompute the entire history of those particles when they want to go to where that particle is at time n. So it's because they're trying to make this whole thing sequential or recursive is the reason that we go from n to n minus 1. But that's not usually stated. At least I haven't seen it stated anywhere. It's an implicit decision, and it drove me nuts to really think through, like, why on earth would they do this? And I think I finally figured it out. I mean, I guess even that's speculation, but I think it's accurate. There's a second design decision that they've made, and I've highlighted things in blue so you can see where this is going. Technically, when we're thinking about this part of the importance density, it can be conditioned on the entire past value of the states, as well as all of the entire history of measurements, up to and including the current measurement. We could. You know, when we're applying Bayes' rule, we can make this thing anything we want. We get to pick it. And so we could condition it on all this stuff. But if we're going to do it recursively, we don't want the density that we're using to advance the particle from time n minus 1 to time n to depend on the entire past, because then the computation would scale with time. So the reason to make this only dependent upon the state at time n minus 1 and the measurement at time n is simply because that enables us to, again, make this recursive. So that when you've got your particle, you can advance it one step forward without having to worry about your entire past. So the rationale really for all these design decisions is the same. It enables us to represent the importance density in such a way that we can do it recursively. And there's bad consequences of these decisions that are also overlooked. But I'll get to that in a bit. But that's the reason, as far as I can tell, those are the reasons why when you look at the importance density and they factor it wrong, it's not that they factored it wrong, it's just that they decided to make some simplifying decisions in the choice of these probabilities such that it can be done recursively.
So
Andy?
2 questions is, one, but we're still able to sample from this because we need to be able to do that.
Yeah, that's right. So we've made it simpler though by factoring the probability in this way. If we know what a particle is at time n-1 and we've got our measurement at time n, all we need to do is formulate this probability such that we can draw a sample for what x of n is. We no longer have to think about generating an entirely new trajectory every time we get a new sample.
Yeah, which we can do from the process equation and the model one.
Very good. Yeah, exactly.
And then the second one was just, this is still letting us get the joint posterior probability density and not just the marginal.
Yeah.
Okay.
Yeah, it's cool. It kind of comes for free. Yeah, it does. So this is nice. And again, we get to pick this Q. And that choice is important. It's not as important as some other things, but it's an important choice. But we can pick that. And so right now, what you can have in your mind is, let's do a Gaussian distribution. That was picked earlier, and everyone likes sort of Gaussian random number generators. So for right now, you can think, I'm just going to make it Gaussian because that's simple, and who cares? It's got infinite support everywhere, and the math works out. So for now, you can think of this as Gaussian. We'll make that better later.
So I may not be understanding the concept of the importance function correctly, but doesn't it kind of make sense that at least the x term only depends on the previous state because it's the process that you're trying to model is a Markov process?
Right now, we're not trying to model a process. Right now, we're just trying to figure out how to draw particles. Mm-hmm. And we're really doing it without much guidance yet about what happens if we choose poorly. We don't even really know what it means to choose poorly yet. We will, but we're not there yet. So right now, this is really completely decoupled from our state space model. It has no relationship to the state space model at this time. It's a density, and the only special property it has, because of these 2 design decisions we made, is that it can be done recursively. So if you've calculated over time, 0, 1, 2, 3, etc., what the value is, that when we want to calculate what it is at time 3, we can advance from where it was at time 2. We don't have to go back and recalculate the entire trajectory from 0 to time 3. So we've made a recursive importance density. The recursive part of this is really the only thing we've accomplished and the only property we need right now.
Are there any alternate representations for the constraints these assumptions place on Q, on the choice of Q?
I haven't seen them. I've wondered about that myself. What if you didn't make this choice or didn't make this choice? Does that provide some opportunities or some performance gains possibly? And I don't know what the answer is. I've never seen anyone do it, but although I'm teaching a class on state-space tracking, I don't claim to be an expert on particle filters, and so it's totally possible that in the literature there are people that have thought more deeply about this and come up with it, but they're not heavily cited. If they have, I can tell you that.
I could see if you wanted to do smoothing instead of filtering, then obviously you don't want to just depend on the past history. You probably want to do some kind of bi-recursive depend on the one in the front.
Well, but right now we're not. I mean, we could have generalized this and said, well, what if it goes in the future? But it actually doesn't matter. We'll see. We can do smoothing, it turns out, with particle filters quite easily. But the importance density, it probably still makes sense to calculate that recursively because it's efficient. So even if you wanted to do smoothing, we're not talking about factoring the posterior. It's just the importance density. Okay. And the only reason we factored it this way is so that we can efficiently advance it in time. So even if we want to do smoothing, this may still be a reasonable decision to make.
What if it was recursive but didn't have infinite history? If you chose like the previous 5 samples or something as being part of your importance
Well,
calculation?
this is where there gets to be a difference between this decision, going from this equation to this equation, and going from here to here. This one's more problematic because this changes the thing that you start with. This is not what Q was at time 0 to n minus 1, because this depends on what the measurement is at time n. So it's not recursive unless you make this 0 to n minus 1. And so it's basically this at time n minus 1. You can't advance it unless you do this. But in terms of what you condition this on, there's absolutely no problem at all on making this sort of a fixed lag thing, where maybe this does depend on the last 5 measurements, or possibly on the last 5 values of the state. That wouldn't be a problem at all. And that would still provide computation that doesn't scale with time. So yeah, that would certainly be perfectly permissible. But I don't know exactly how you would do it, but there would be no problem with that. Great questions. Okay. Sure we don't cover too much. So the task remaining, if right now you think, okay, I've got an importance density, it's recursive, I'm going to choose Gaussian, that's easy. So every time I'm just advancing my particles 1 point into the future by picking a Gaussian random number, and that's the next value that particular particle trajectory takes on. So that's one way in which you could factor this Q. Our weights are the ratio of the posterior relative to our recursive importance density. And again, we get to pick this, so you can think, oh, the particles then, I'm picking where the particles come from, and I'm picking them from a random number generator. Like, what could be simpler? Just fire up your random number generator, and the only thing left then, for now, is to figure out what are the weights. And again, we'll talk about good importance densities a little bit later, but for now, just think, okay, we've got our particles, we just sequence of Gaussian random numbers, how do we calculate our weights? If we have those, we've got our representation of the posterior, we now know how to calculate the mean from that representation. So math, and you'll be glad to know I dropped all the I superscripts on this slide only because it just simplifies the notation a little bit, and I don't think anything is lost in doing it. So although we're really talking about the ith weight for the ith particle, for the purpose of this math, it works even if we're not, even without that I, so I dropped it. So this is the same as what we had on the previous slide. It's the same as what we had from Monte Carlo integration, except now, rather than this being P of x, it's the posterior that we're actually interested in. And our importance density can be expressed in the same form, but it's something that we pick. We know that our posterior can be expressed from the optimal Bayesian equations is the likelihood times the prior times the previous posterior divided by this normalizing constant. And this whole thing is proportional to these 3 terms on top. I'm just dropping this bottom term because it doesn't depend on x. And so this is where, we have that constant term that we're going to have to deal with by normalizing the weights downstream. So now what we're actually working with is not the actual posterior probability, but something that is proportional to that posterior probability. And our importance density, because the design decision we made also factors into a product of 2 different terms. And one of those terms is the past of what it was. So if you substitute in this equation and this equation in what we started with, now we end up with weights that are proportional to, they're no longer equal because we got rid of this term, but we end up with weights that are proportional to the likelihood times the prior times the previous posterior divided by whatever we choose for this part of the importance density times the importance density at the previous time step. And if you just factor this a little bit differently, collect these 2 terms and push them to the right so they're in their own ratio, if you look at this carefully enough, based on our starting definition, this ratio is just what the weight was at time n minus 1, which is awesome because that makes our equation for the weights recursive. The way in which we calculate the weights is now a recursive equation that we can handle efficiently. So we end up with, once again, I hope I don't overuse this term beautiful, but this is a beautiful recursion where the weight of the ith particle, I've added the index back in, the weight of the ith particle at time n is proportional to, it's not equal, but at least it's proportional to the likelihood, which you all now have experience calculating on homework 1 and 2, the prior, which you have experience calculating on homework 2, and you've seen examples in lecture, divided by the importance density, we got to pick it, call it Gaussian, times what the weight was at time n minus 1. Great. Great, we've got it. We've got a recursion for our weights. So you pick the importance density, you can get your likelihood from your measurement model. You may have to do a little bit of work if it's not additive noise. If it's additive noise, it's easy. Same thing for the process model. You can get your prior directly from the process model, as we've talked about before. And if you know what the weight is at your previous time step, then you've got this equation by which you can now update it, or at least end up with what your weights are before they're normalized, within a normalizing constant. So that's kind of it, right? I mean, you kind of have it. And now sorry about the typo, marginal posterior is our estimate. Our estimate of the marginal posterior is now defined as, when you see that little triangle on top of the equals, I'm using that to simply mean that I'm giving you a definition. So this thing on the left is defined as this weighted sum of, or weighted average of impulses, where the weights are particle weights, and the particles are at the random locations that you put them at. And that's in some respects, that's it. But right, we still need the marginal posterior. This is the joint posterior, so we're not quite there. So we need the marginal, but you know what? It's easy. It turns out, because our joint is this weighted sum of impulses, where these impulses are this multidimensional product. But if you say, well, one way of getting the marginal is to simply integrate out everything except what you want to retain. So we integrate out the state from time 0 all the way up to time n minus 1. But this integral ends up being easy because we're just integrating impulses that have unit area. And so what we end up with is essentially the same equation. The only difference is this is now an impulse function of x of n minus wherever the particle is at time n, whereas this was the entire trajectory. But the weights are identical. So we end up getting both, which is kind of amazing. We've got the marginal, we've got the joint posterior, we've got a very simple parametric representation of both the joint and the marginal. If we only care about the marginal, all we need to carry along are what the weights are and where the particles are located. And again, those are random numbers you generate. So pick 500, 500,000 of these, it doesn't really matter. It's a finite number that you get to pick. So, in some respects, it would seem like, okay, awesome, we're ready to go. And here is the loathed sequential importance sampling algorithm in its simplest form. So this is kind of a notation that's used. If this is a recursive equation, to go from knowing what your particle is at time n minus 1 for the ith particle, I equals 1 to np, you can do it over all of them, and your weight at time n minus 1, given that you've got a measurement at time n, the way you advance that to what your estimate of the state is, what your particle is at time I and what your weight is at particle I at time n and your weight I at time n, it's very simple. Draw these from a random number generator that you pick, say it's Gaussian, and use that recursive equation that you know now how to evaluate to calculate what your weights are at time n from time n minus 1, and then normalize them. And remember, these weights are scalars, so this is not cumbersome. These are vectors, but these are simply scalars. So calculating this is a flash. It's really fast and it's really easy. And that is the simplest and the first particle filtering algorithm. And it's not far from what will actually work. I mean, in practice, this ends up having a fatal flaw and it doesn't work, but we'll fix it on Tuesday. And you'll see what that flaw is, and we'll fix it. But here's your first particle filter algorithm. Any questions? Yeah, you don't have to. Sorry. Yeah. Thanks. Right. There's like that
Waiting for the
heavy pause. Like, come on. It's a big deal. Feel it. Any questions or thoughts about that? For those of you that have not yet read ahead and don't know what's coming, for those of you that haven't or looked ahead in the slides, does any guess on what the fatal flaw is going to be?
resample or something.
Something like that. Yeah. All right. But that's a good stopping point. So I will update the next homework, so let's do a week from Tuesday and not next Thursday. And I'll see you guys on Tuesday. So have a great weekend. Do some reading, please.